In this problem, we are given another differential equation, specifically that the velocity is changing according to this function, negative 2v minus 32. This is for a falling skydiver. So this is a physics problem that uses a differential equation. So we have that dv dt is equal to negative 2v minus 32. And as with most of these differential equation problems, we want to see what methods we have available to us to solve it. The first thing we might want to try to do is see if we can use an antiderivative to do this. Unfortunately, we can't do that here because if we just if we multiply both sides by dt, we get dv is equal to negative 2v minus 32 dt. If we try to take the indefinite integral of both sides now, we see that we have two variables. We have a dt here, and we have a v there. So that doesn't work. So we can't just use an antiderivative for this. This means that separation of variables is our only option. So to use separation of variables, we need to see if we could potentially write this differential equation, the right-hand side, as a function of v times a function of t. Now this is not that hard to do because we can look and see that this entire right-hand side here is a function of v. So our function of t could just be 1. If that is the case, that makes things much simpler. So since this 2v minus 32 is our function of v, and this 1 is just our function of t, we can move forward and use separation of variables. So dv over our v function, that would be negative 2v minus 32, is equal to 1 dt. Okay, so with our variables correctly separated, we can now use our indefinite integrals to solve this. So our right-hand side is pretty straightforward. This just becomes a t, and we'll add in a constant on the left-hand side. On the left-hand side, we need to come up with an integral of 1 over negative 2v minus 32 dv. Now we could use substitution to help us with this. We could say u is equal to negative 2v minus 32, and then take the derivative of both sides and find the differential. Du is going to be equal to negative 2 dv. So this means then that we can get dv by itself by multiplying both sides by negative 1/2 du. So that becomes what we substitute in. So our integral then becomes the integral of negative 1/2 du, because that's our dv here, divided by negative 2v minus 32. We can pull that negative 1/2 out, so negative 1/2 times the integral of du, and we can substitute for this, which is just u, so negative 1/2 the integral of du over u. And we know that that indefinite integral is just ln of the absolute value of u. Let's, as a last step, then substitute back in for u and get the absolute value of negative 2v minus 32. Let's take this and substitute it back in to our expression over here. So this becomes negative 1/2 ln of the absolute value of negative 2v minus 32 is equal to t plus c, and simplifying this a little bit, ln of negative 2v minus 32 is equal to negative 2t minus 2c. Let's use that exponent property, that relationship between logarithms and exponents, to now say that the absolute value of negative 2v minus 32 is equal to e to the negative 2t minus 2c. And I'm going to take that right side and rewrite it to say that this is e to the negative 2c times e to the negative 2t. And I'm also going to say that this absolute value here, I'm going to get rid of it and get rid of it by putting that plus or minus in there. And the last thing I'm going to do to make things easier is I'm going to divide everything by -2 to get v plus 16 is equal to plus or minus 2 e to the -2c. Sorry, that should be plus or minus 1/2 e to the -2c times e to the -2t. Now that looks like a lot of work. Why did I do that? Well, I can take all of this and combine it into a single new constant and just say, let's make this new constant a, and that becomes a e to the -2t, and that is equal to v plus 16. And now I can just solve for v and get that v is going to be equal to a e to the -2t minus 16. So now I have solved for v. Whether it's plus, whether it's minus, all of this messiness that's inside this constant, it's all contained within that a, and all I need to do is use the initial condition to figure out what that is. I know that at t equals 0, I know that v of 0 is equal to -50. So I can substitute that in for v. So -50 is equal to a e to the -2 times 0 minus 16. And that just means -50 is equal to a minus 16, which gives us that a is equal to -34. And that brings us to our solution of saying that v of t is equal to -34 e to the -2t minus 16. So that is our answer for part A. If we go up, the second question says terminal velocity is defined as a limit as t approaches infinity of v of t. Well, for B, we want to find the limit as t approaches infinity of this expression, -34 e to the -2t minus 16. So we could graph it, we could use our limit rules, we could also just know that the property of the exponential function here is that this function right here will tend to approach 0 as t approaches infinity. It gets smaller and smaller and smaller and smaller and smaller, which means that the limit as t approaches infinity is just going to be -16. The last thing is that it is safe to land when her speed is 20 feet per second. At what time t does she reach this speed? This requires that we just solve an equation. So we take this v of t. V of t, we are told, is equal to 20 feet per second. And that's the speed. So this is really the absolute value of v of t is equal to 20. Because this function, if we think about it, is it always has a negative value, that means really that v of t equals -20. And so we set that equal to our expression for the velocity function. We can use a little bit of algebra from this to see -34 e to the -2t equals -4. E to the -2t then is equal to 2 over 17. Use our log properties. -2t equals ln of 2 over 17. So t is equal to -1/2 ln of 2 over 17. That would be an exact value. We could also use some decimals if this was a calculator active question to find what that value is.